So take your calculator, please, and we're going to experiment just a little bit with the calculator, see what we can come up with. What we want to know here is what effect does A have on a quadratic graph? Remember, y equals ax squared. We want to go in our graphing calculator and change the value of A a little bit. Maybe trying a fraction or an integer to determine what effect does A have on that quadratic graph. So what I'd like for you to do is plug some values into your calculator. We'll start out with the parent function here, f of x equals x squared. Just put that in first and then try some of these others. You can graph them on top of each other. You can do one, stop it. But spend just a few minutes, if you're watching the video, just stop the video and spend a few minutes exploring. Let's talk about a couple of things as you've been investigating that. First of all, let's look at f of x equals x squared. That's the most fundamental quadratic function, the basic, the simplest quadratic graph. By the way, what do we call that? Do you know? Do you remember? You know what we call that? It's called the parent function. The simplest one there is. And the parent function is, and I'm just say it in terms of y equals x squared, okay? The parent function will always have the same values. We've already looked at a table that it does. For example, if x is -2, -1, 0, 1, 2, these values are 4, 1, 0, 1, and 4. Okay, that never changes because that's the parent function. If I looked at that on a graph, then in my graphing calculator, I would put y equals x squared, and I would graph it. So there's what the parent function looks like. It's going to graph in blue. So your mission was to take and try different values for A. Remember that A is the coefficient in front of the x squared. And I said try one. So let's try one that looks like this. Let's try y equals, and this time I'm going to say 5x squared. I'm going to do that. Okay? So if I put that in the graphing calculator, this time I'm going to use, I like this calculator because it'll do it in colors, graphic colors. So I'm going to go down here and graph it in red. So it's going to be 5x squared. Now see if you can tell me what's different about that graph. What do you notice about that graph? What do you see in that graph? How does it look different? Because the value of A was 5, then that parabola got skinnier, or we call it a vertical stretch. Let's take it and look at another possibility here, okay? Let's take it and look at one. This time, let's let A be a fraction, okay? So y equals maybe 1/4 x squared, like that. First of all, before I put that in the graphic calculator, what do you think the graph will look like? You know, when it was 5, it became a skinny graph. What do you think a fraction will do? Do what?
Oh, it'd be big, wouldn't it?
Could be. Let's see what happens. All right, so I'm going to go down here. I'm going to graph this one green just because the colors are going to stripe. So I'm going to put in 1/4. And remember, I told you that when you go graph it, you want to say that my fraction is in parentheses. You have to always graph the fraction in parentheses. So they all give, we'll say x squared. And we'll let that graph it. Now check it out. All of you are right. That graph is one that is wider. It's actually what we call a vertical compression. So based on what we've just seen, when A is greater than 1, it's a multiplying factor. And so it stretches the graph. But if A is less than 1, like a fraction, then it is a compressing factor. It's actually dividing the y values of whatever fraction it is that we're multiplying by the fraction, but we're really dividing by the denominator. So it compresses that parabola. Well, that's really an important thing because it's a predictor. It kind of tells us what the graph is going to look like. In fact, we can use it to graph them quickly and easily based on what is that value of A, how does that change the graph. So when A is 5, it's a multiplying factor. It increases my y values. Well, what about if A is that fraction we talked about here? Then it is a dividing factor. In other words, 4 here times 1/4 is 4 divided by 4, or 1. And 1 times 1/4 is just 1/4. So my coordinates are -2, 1, and -1/4, of course, 0 times 1/4 is still 0. That never changes. So you see how when A was a fraction less than 1, my y values are compressed. That's important to know. Let's talk about a little different problem. We've kind of got an idea of how A affects the graph. Remember, if A is greater than 1, it's going to vertically stretch the graph. If A is less than 1, between 0 and 1, if it's a fraction that is less than 1, then it's going to vertically compress that graph. And we've already talked about several times over that if A is positive, it opens up. If A is negative, it opens what? Down. Everybody say down.
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 Yeah. So let's look at a little different problem. But with a lot of the same ideas there. This says to determine the equation. And when I say determine the equation, basically what I'm going to do is I'm going to write an equation. I'm not going to jot that down. Now, just by inspection, I know that this quadratic opens down, so A is going to be negative. Also remember that the parent function is y equals x squared, but this has got to be some change from y equals x squared. So we're going to need to find out what is the coefficient of x squared. And is it a vertical stretch or is it a compression? Well, if I kind of pencil in the parent graph, I know that the parent graph has the values of 0, 0, 1, and 1, 2 and 4, just like that. So here's the parent graph. So when I look at the parent function, then I see that the parent function is a little smaller than the function I'm trying to find A for. So A must be some kind of fraction. Still not quite sure what. It must be less than 1, so we're going to figure that out. All right? So let's see, how do we do that? What other piece of information do I have on here besides that the vertex is at 0, 0, the y-intercept is at 0? What else do I see there? There's one other piece of information I'm not addressed here. See it? What is it?
The maximum is 0.
What?
The max is 0.
It does have a maximum, but that's not that's not what I'm trying to draw your attention to. There's another part there. We're given some coordinates of a point that is on the graph. Do you see that? You see where that's at?
4, -8.
Yeah, it's 4, -8. Check it out. Okay, so here's what we know. 4 is x, and y is -8. I can use that information. Here's how I'm going to use that information. We'll go back to y equals ax squared. And for x, I'll plug in a 4. And I'll go here and I will say, okay, that's going to be 4, just like that. All I did was substitute that 4 for x, write that down. And y is a -8. See what I did? Write that down. So 4 squared is 16. Here's a, so 8 times 16 -8. Actually, I would rather write my variable to the right, so I could write it this way. -8 equals 16a. I know if I want to solve for a, what I'm trying to find out is what is that value of a? Okay? But I know I have 16 times 8 to solve, I just divide by 16 on both sides. That's -8 over 16. That's a fraction that's reducible. And that fraction reduces to be -1/2. So after those cancel, A, I discover, is -1/2. Well, that makes sense because it's a little bit compressed, a little bit wider graph than the parent function is. I knew it had to be less than 1. 1/2 is less than 1. So compress it. So to write the equation then, all I have to do is I found this -1/2 for A. I'm just going to put that in for A. And it's y equals -1/2 x squared, just like that. And I've written the equation. So the key is take what information I know, use it to find A. I can write the equation. That's right. Let's look at another example. So same basic deal. I've got a graph, but I don't have an equation. I've got a point, and the parent graph I know is 1, 1 here, and 2, 4. And so if I kind of sketch in the parent graph, I realize that this one is not a lot, but it's a little bit skinnier than the parent graph. So it must be a vertical stretch. So I'm going to approach it the same way. I remember it's y equals a x squared. I'm going to write this down. And I'm going to substitute the values 2, 5. I know a is going to be positive because it opens up. So I get 5 equals a, and then for x I'm going to substitute 2 and square that. Well, that'll be 4a. And now I divide both sides by absolutely. And so a is equal to 5/4. Well, 5/4 is an improper fraction. It is greater than 1, so it does work. It does stretch the graph. That's what I thought it did. And so to write that equation is y equals 5/4 x squared. The key is all I have to do is take that point, find that value of a. And it makes sense. Makes sense because 5 fourths is a value greater than 1. So it's a little bit of a stretch. Not much, a little bit. We'll wrap this up with one additional example. This is a real life example. You'll want to write a few things down here. First of all, this is the problem. It's talking about a slingshot. How many people have ever shot a slingshot? Have you ever raised your hand on this? Okay? So you kind of have an idea how that works, right? You pull it back farther, pull it back, the harder that it shoots. In fact, what this is telling us is that it stores energy based on how far back you pull the slingshot. The farther back you pull it, the more energy that's there. And the more force that whatever object you're launching with that slingshot, the more force it will have. Well, the first thing says, describe what the vertex and the y-intercept. Okay, so the vertex and the y-intercept. Tell us what those represent and what this endpoint here, what it represents. So let's talk about that a little bit. First of all, if I'm going to talk about the y-intercept, I probably need to look at how my y-axis is labeled. So basically, the y-axis is telling me how much energy is stored. When I pull it back, a pull length, and it changes. It's actually a parabolic curve. The farther I pull it back, the energy increases quite a bit, actually. So let's talk about what the vertex means and the y-intercept. The vertex simply means, you'll need to write this out when you're given a homework problem. The vertex means there is no energy when it is not pulled back. Likewise, the y-intercept it's the pull before it's being pulled. Let's pull it back. Zero centimeters. It has, the y-intercept represents that it has no or zero energy. And that endpoint represents, remember it was a value of 2,200, so the endpoint means when you pull it, back 20 centimeters. You will have 200 millijoules stored energy. It's important to know what everything means in a real life problem. Now, if we go back and we look at the problem, the next stage is to say, well, let's write a function that represents that. So we need to really go back and look at the graph. after we've defined all those things. And in order to write a function, you remember that the function will be written y equals ax squared, but I want to put it in function notation, the function of E standing for energy. So this function will look like this, and we'll write it with function notation and substituting the y for the energy in respect to D, and then we'll also write equals AD squared. That's okay, we'll make those conversions, nothing different really there. What I want to figure out then is what is the value of A? And so for Y, I will substitute 200, and for D or X, I'll substitute in that value 20, and I'll need to square that value. And that's 400, so my function becomes 400 A, and I'll divide both sides by 400. When I do that, I can reduce the fraction 200 divided by 400 because that's actually the fraction of 1/2. All right, so when you think about it, the 200 is half of 400, so that makes sense. So to write the function the way I need to, write it this way. And the trick was finding the value of A. So to recap, what I'm really focusing on today is how A affects the graph, how I can use A to write an equation given just a single point on a parabola. I can do that because these parabolas we've been looking at have had a y-intercept and the vertex is 0, 0. So finding A is kind of simple as long as I have the other points.